Institute. So Honda-san is he will tell us about digital quantum simulation of higher Schwinger model with topological term. Okay, please start.
Okay, thank you very much for introduction and the invitation to the wonderful conference. I'm Masazumi Honda from Yukawa Institute for Theoretical Physics in Kyoto. I'm going to talk about digital quantum simulation of a higher charge Schwinger model with topological term. This talk is based on the following three papers. These are based on collaborations with Vipasha Chakraborty, Yuta Kikuchi, Taku Izubuchi, Akio Tomiya, Rento Nagano, Takuya Okuda, Etsuko Ito, and Yuya Tanizaki. And let me start with introduction. First of all, this talk is different from most of other talks in this workshop from two perspectives. First, I'm working on high energy physics, and this talk is not about tensor network, despite this workshop is on tensor network. This talk is about application of quantum computation to numerical simulation of quantum field theory. But we have a common motivation, which is to circumvent sign problem, infamous sign problem in Monte Carlo simulation. And in the context of high energy physics, sign problem physically occurs when we analyze systems with real-time chemical potential and topological term, and so on. So, long-term goal of project in this direction is roughly like this. So we have a quantum computer, and finally, I'd like to analyze the world of elementary particle, universe, and so on. But in particular, in this talk, I focus on a model called charge Q Schwinger model with topological term. This is 1+ one-dimensional quantum electrodynamics with charge Q Dirac fermion. And Lagrangian is given by this. First, we have a kinetic term of gauge field, and we also have a kinetic term of fermion, and we also have a mass term of fermion. And the second term is a topological term called theta term. And I put the charge Q here, and we will see that the charge Q will play an important role physically. And this model is supposed to be difficult in the conventional approach by Monte Carlo simulation because we have a real time. And also, even if we consider imaginary time, we have a sign problem when theta is not small, because this will give a complex action in the Euclidean case. And concretely, we got the following result. First, we constructed vacuum or ground state of lattice version of this system, and we computed expectation value of fermion mass operator and the continuum limit, and we got the consistent with previous calculation and get prediction. And we also explore a problem called screening versus confinement problem, explained in next slide. And also, we have seen that potential between charged particles sometimes get behavior called negative string tension behavior. Okay, next, let me briefly explain screening versus confinement problem. Let's consider potential between two heavy charged particles in this model. And we are in 1+1 dimension now, and the classical picture is like this. So we have a Coulomb law in 1+1 dimension, which gives a proportionality with distance. And 1+1 dimension is special because Coulomb law is the same as a picture of confinement. Since we have a linear behavior, but this expectation is too naive in Schwinger model because we have a dynamical frame. And it is known that behavior of potential changes qualitatively as changing charge of probe and charge of dynamical fermion. And there are analytical results by some technique in this model. First, if we consider massless case, it is known that the potential behaves like this. So this is quite different from linear behavior. And this gives a screening behavior. So for long distance, potential becomes flat. And massive case is more interesting. It is for small mass, by mass perturbation, people got this potential. So it seems we have a linear behavior, but coefficients can change qualitatively as changing Q and QP and theta. First, if QP probe charge is proportional to integer of charge of dynamical fermion, the coefficient becomes 0, and we again have a screening behavior. And if QP is not the integer times Q, it seems that we have a linear behavior, but the coefficient is not positively definite. Sometimes we have a negative slope. So this sounds quite interesting. And this is based on analytical computation for small mass case. But if we can do numerical simulation, we can also explore larger mass region. So let's explore this aspect by quantum simulation. So these are what we are gonna see. Next, I will explain how we rewrite the Schwinger model in terms of qubits. And then I will explain how to prepare ground state or vacuum of the Schwinger model. And next, I will explain the result with Q=1 and case without probe charge. And then we will put higher charge and higher and probe charges. Okay. So next, let me start. Let me explain how to rewrite the Schwinger model in terms of qubits. Qubit. What is a qubit? Qubit is a quantum bit, and qubit is physically a quantum system with a two-dimensional Hilbert space. And there are many ways to realize a qubit. Typical one is up-down spin system. And quantum computer is a combination of qubits. And if we want to put quantum field theory on quantum computer, we have to do the following two things. First, we have to regularize the Hilbert space because the Hilbert space of quantum field theory is typically infinite dimension. And after we get the finite dimensional Hilbert space, we should rewrite the regularized theory in terms of qubits. And the Schwinger model is the simplest non-trivial example with gauge interaction in this context. First, we have a gauge field, but in 1+1 dimension, gauge field is not propagating, and we have only one dimensional physical Hilbert space. And also, if we cut the space by lattice with finite point, then Hilbert space of fermion becomes finite dimensional. So physical Hilbert space of a Schwinger model on lattice is finite dimensional. So in this sense, this is the simplest non-trivial example in this context. And if we consider bosonic field with physical degrees of freedom, propagating degrees of freedom, we need additional treatment. But I do not explain this point in this talk. And this is the Lagrangian of Schwinger model. We have a gauge kinetic term, topological term, fermion kinetic term, and fermion mass term. And if we take temporal gauge, A0 equals 0, we get the following Hamiltonian. Phi is the conjugate momentum of gauge field. And the physical states are constrained by Gauss law given by this. And this is a continuum description. And since this is 1+1 dimensional, some region can be accessed by analytic computation. First, if we consider massive limit of fermion, then the fermion is decoupled, and the theory becomes effectively purely Maxwell theory, which is free theory. So we can solve when mass is very, very large. And another thing is that we can use a technique called bosonization. I do not explain detail, but it is known that the Schwinger model is dear to this model. Phi is scalar field. So I forgot to put Q. In this picture, the fermion mass plays a role of coupling, self-coupling of the scalar theory, and G plays the role of mass. And therefore, this model is exactly solvable for m equals 0. And small m regime can be approximated by perturbation theory in this model. And if we want to analyze this model by Monte Carlo simulation, we have basically have a sign problem when we consider non-zero, non-small theta. First, in Minkowski space, for a real-time case, we always have a sign problem because Boltzmann factor is exponential of I times action. And even if we consider imaginary time case, we have a complex action, and we have a sign problem when theta is not small. So in summary, we have this map of accessibility or difficulty. So we are in the space of fermion mass and the theta angle. And first, at the origin, we can solve the theory exactly. And for large mass, the theory can be approximated by pure Maxwell theory. And when theta is not small, we can access by Monte Carlo simulation, standard Monte Carlo simulation. And but in this region, this region cannot be accessed by both analytic computation and standard Monte Carlo simulation. So we can make prediction here. All right. So next, let me try to put the theory on lattice and rewrite the theory in terms of qubits. First, we have a fermion. We put the fermion on side, and originally fermion had two components, and we put the upper component and the down component on different sides. And this method is called staggered fermion. And we also have a gauge field. We put the gauge field on link. And phi is corresponding to gauge field, and L is basically corresponding to the conjugate momentum of gauge fields. So pictorially, we have a degrees freedom on lattice like this. So we have a fermion on side and gauge field on link. Then in this formalism, Hamiltonian of the lattice Schwinger model is given by this. This one is a gauge kinetic term, and this one is a fermionic kinetic term. And we also have a fermion mass term. And we have a theta angle, and we have a charge of fermion Q here. And W is basically inverse of lattice spacing, and J is gauge coupling. And we have a commutation relation. And this is a Gauss version of, this is the lattice version of Gauss law. So the right-hand side is basically a charge of fermion. And to rewrite the theory in terms of qubit, we first eliminate the gauge field. Here we take open boundary condition, and then we can solve Gauss law. And so we can rewrite gauge field in terms of fermion operator. And also we take gauge UN equal 1. Then Hamiltonian is given by this, although this looks complicated. And now we have only fermion operator, lattice fermion operator. And the first line remains the same, but the second line is changed because of solving Gauss law by this. This was originally gauge kinetic term, and solving Gauss law induces non-local interaction between fermions. Anyway, now we have, since we have only fermions, we have a now finite dimensional Hilbert space. And next, I'd like to insert the probe charges. And normally in Lagrangian formalism, probe charge is introduced by inserting long rectangular Wilson loop. This is Wilson loop. And if we use Stokes theorem, we can rewrite Wilson loop by using field strength. But this form is the same as theta term defined locally. So this is theta term with theta equal 2 pi qp. And here we include the effect of probe charge into the action and switch to Hamiltonian formalism. So we have a spatially varying theta term like this. Then we compute the ground state energy in the presence of probe. So in this way, we can compute the potential between probe charges. Okay, and if we insert probe charges, so theta angle becomes spatially changing. And also, I'd like to map the theory to a spin system in order to make a connection to qubit clear. And there are many ways to do this. And here we use the most traditional way called Jordan-Wigner transformation. Especially this is given by this map. And here X, Y, and Z Pauli matrix are put at site N. then the system becomes purely a spin system like this. So we have a z-z interaction and x-x interaction and y-y interaction. So this is similar to xy model with but with a spatially dependent longitudinal magnetic field and some non-local interaction. So it looks complicated, but anyway, in this one, we can naively apply algorithm used in quantum simulation for spin system. So this is a qubit description of the Schwinger model. So next up, I'll explain how to prepare ground state of this system. Before that, let me briefly explain idea of quantum computation. To me, rule of quantum computation is as follows. There are two important operations in quantum computation. One is the action of unitary operator. We are going from left to right. And another one is a measurement, which assigns a classical number with some probabilities from the state. And to me, rule of quantum computation is to do something interesting by combining the following two operations. And this is the atmosphere of using quantum computation. This is a screenshot of a website called IBM Quantum Experience, where we can use a quantum computer in cloud easily. And suppose we'd like to measure the following state. Here H is called Hadamard gate. And in this website, we can create, we can make quantum circuit by drag and drop. And this is a gate for measurement. And then we can get a histogram of probabilities having each computational basis inside the state. So idea is to express physical quantity in terms of probabilities and measure probabilities. So roughly speaking, this is the idea of quantum algorithm. And so then how can we prepare ground state of the system? And there are various algorithms to prepare ground state. And in this talk, I adopt an algorithm called adiabatic state preparation. So in this method, we start with initial Hamiltonian, which is a typical different system from target system. So we choose initial Hamiltonian H0 of a simple system whose ground state is known and unique. Then we introduce adiabatic Hamiltonian, which connects initial Hamiltonian and target Hamiltonian. So we have a target Hamiltonian at final time. And it should be slowly varying when the parameter is very, very large. Then we use the adiabatic theorem, which claims that if adiabatic Hamiltonian has a unique ground state with a finite gap for any t, then ground state of target Hamiltonian is obtained by the following time evolution. So this is the idea of adiabatic state preparation. But in practice, we have to discretize the integral to the product. So practically, we have to evaluate. We have to match evaluate this one, and we also apply Suzuki total decomposition for each object. And concretely, we choose adiabatic Hamiltonian in this way. Basically, we start with a massive limit of the system, and we gradually change the parameters to the target Hamiltonian. And this is our algorithm to prepare vacuum. Next, let me show our numerical result for Kiko 1 without the probe charge. And before that, I have to explain something on real quantum computer and classical simulator. So in real quantum computer, qubit in the quantum circuit is not an isolated system, and we have a interaction with the environment, and then we get errors. So in order to get the precise result, we have to correct errors. And here we use a simulator, which is a tool to simulate quantum computer by classical computer. And this does not have errors, and we can get ideal answer. But we cannot have speed up because we are using classical computer. But this is useful to test the algorithm and estimate computational resources for quantum simulation. So this is a nice first step to apply quantum algorithm to numerical simulation in future. And here I'd like to compute the expectation value of mass operator. And if we after Jordan-Wigner transformation, the operator is given by this operator. And then once we get the vacuum by some algorithm, we can compute the expectation value in this way. So we can express the expectation value in terms of probability having each basis inside of the vacuum. So in this way, we can compute the expectation value of this operator. Okay. And this is a result of the expectation value of mass operator, fermion mass operator for massless case. And we have already taken thermodynamic limit and continuum limit. And we have chosen parameter like this. Here, T was the final time of the adiabatic state preparation, and delta T is a step of total decomposition. And N is basically the number of qubits or number of sites along spatial direction. And this is a plot against the plot of expectation value of fermion mass operator against gauge coupling. And the red line is exact result by analytic computation using Bostonization technique. And we see that we have agreement within errors with exact result. And this is a result for massive case. We fixed gauge coupling, and we plot the chiral condensation against the fermion mass. And we computed both for theta equals 0 and theta equals 3 pi over 5. For theta equals 0, we can use Monte Carlo simulation. And the straight lines are result of mass perturbation. So we see that when mass is small, we have an agreement between numerical result and mass perturbation, and but as changing mass, we have a deviation. And for this case, there are also results by tensor network approach, and we basically have agreement. And the green symbol is a result for non-small theta, and similar to theta equals 0 case, we have an agreement for small mass, but we have a deviation for large mass from mass perturbation theory. And the result in this regime can be regarded as a prediction from our simulation. And next, let us consider higher charge of dynamical fermion and put probe. Okay, and this slide is a repeat of the slide in introduction. So we have a good analytical computation when mass is small. For massless case, we have a screening behavior, and for massive case, we have different behaviors depending on probe charge and dynamical charge and theta. And before showing a numerical result, let me comment on some frequent asked questions on negative string tension behavior. First, it sounds that negative tension behavior implies that pair creations of fermions are favored, and favored, and it sounds that the theory is unstable. And the answer is no, because as we can see from this equation, negative tension behavior appears only when Qp is not the integer times Q. So we don't have a pair creation of charges Qp. So such unstable creation do not occur. And another question is that negative string tension seems to imply that we have a lower energy inside probes than energy outside. And energy outside is the energy when we don't have a probes, and it looks like ground state energy. So it seems that we have a lower energy than ground state energy. It sounds strange. And there is an explanation from the viewpoint of symmetry. Although I don't have time to explain in detail. It is known that the theory has a kind of generalization of symmetry called one-form global symmetry, and we have a ZQ one-form symmetry in this theory. And the theory has something like a super selection sector decomposed by the one-form symmetry, and this is called the universe recently. And then inside and outside belong to different sectors decomposed by the symmetry. So the sector inside and outside can be separated. So there is no any contradiction. Okay, so next let me show some results, some numerical results. This is a result for massless case with theta 0 equals 0, and Qp is integer times Q. And we have put parameter in this way. And this is a potential, plot of potential as a function of probe distance. and we have many symbols, and the lines are basically analytic result in the continuum limit. And we plotted result both for different volumes. And we basically have a agreement, although we have some systematic errors here. And this is and this is the result for massive case. And again, we basically have an agreement between the analytical result obtained by mass perturbation theory. And here is a comparison. This is a repeat of the two plots in the last two slides. So we basically have a non-linear behavior of the potential. And as changing volume, we expect that the region here becomes more flat. And this is consistent with the expected screening behavior. And this was a result when QP is Q times integer. Let us consider different case. And this is the result when QP is quarter times Q. And here we have a linear behavior of the potential. By the way, the red symbol is the result for massless case, where we expect the screening behavior. So we have something like confinement behavior. And this is consistent with expected confinement behavior. And it would be interesting to estimate the string tension by picking up the slope of the straight linear behavior. And this is the result of string tension. And we are plotting string tension or slope of the linear behavior as a function of probe charge. And the blue lines, blue symbol is our result, and green line is a result of classical analysis. And blue region is a result of mass perturbation theory for finite volume. So we have a deviation from classical Coulomb behavior, but agreement with mass perturbation behavior. So this implies that so appearing of confinement behavior in 1+1 dimension itself is not so non-trivial, but we have a confinement with tension quite different from classical behavior. So this implies confinement by non-trivial dynamics in this model. And next, let us explore negative string tension behavior. So we have a potential for various values of theta. So we see that depending on theta, we sometimes change the sign of slope. And we also compute the energy density when we have a negative string tension behavior. And the shaded region is inside the probes. So here we have put the probe. So we see that the local energy density drastically changes. Drastically changes as we cross the position of probe charge, and we also have lower energy inside of the probes. So this gives give the negative string tension behavior for this case. And finally, let me comment on adiabatics preparation itself. So it is known that the systematic error of adiabatics preparation is inversely proportional to energy gap of the system with time-dependent system. And there are some advantages. First one is adiabatic. This algorithm is guaranteed to be correct if we satisfy the assumption of adiabatic theorem. And also we can directly get excited state under some condition. And this advantage is that this does not work for degenerate vacuum. And also this algorithm is known to be costly because we typically need many numbers, much number of gates. So perhaps this algorithm is not so efficient in NISQ area in near future. And so if we want to use a real quantum computer, at least in near future, we have to use a different algorithm like a variational based algorithm. Okay, let me summarize. So here we have used the idea of quantum compression to circumvent the sign problem in multiple simulation. But we have to play with huge vectors, huge Hill vector space. And we have constructed the vacuum of Schwinger model with topological term by adiabatic set preparation. And we found the agreement thing for the chiral condensate with exact result at the mass scale and mass partition theory for small mass case. And we explored the screening confinement versus confinement problem and the negative string tension behavior. And but the particular problems in this talk involve only ground states. So it seems that the tensor our approach is not the best, and the tensor network approach is better. And now we are also doing analyzing the same problems by using DMRG approach. And for that case, we can take a much larger volume and we can have a clearer behavior, physically clearer behavior, clearer result. And we are also trying to search critical point at theta, conjecture critical point at theta pi in the Schwinger model. And I like to we are also analyzing we should also apply other methods to prepare vacuum. And this year I'd like to change scattering problem in the Schwinger model or other model. And I'm also interested in analyzing other field theories. And we have to include quantum error correction or mitigation in future. And also I'd like to, so I'm looking for interesting problem which cannot be efficiently simulated both by Monte Carlo simulation and tensor network approach. Okay, let me stop here. Thank you very much.
Okay, thank you so much. Thank you for your nice talk, Honda-san. So the time is open for discussions. So do you have questions or comments? Okay, so Okubo-san, please.
Thank you very much for your nice talk. Can I ask a question about the first result about the mass perturbation? So
for chiral condensation.
Yes, maybe you compare the result with the tensor network.
Yeah.
Yeah. So in this plot, what the error bars means in your simulation. So because your how to say average value is very fit to the mass perturbation line, but the error bar is so large. So what the
Okay. So this is a good point. So let me explain a bit more detail. Okay, first, so there are many various sources of error. First one is since we have only finite number of shots, so we have a statistical error. And another one is a systematic error of adiabatic preparation. And the final one is a extrapolation error of thermodynamic limit and continuum limit. And this one is estimation of systematic error. This is our method to estimate systematic errors. Yeah, and this one, okay, this method is more like a proposal, and so we have introduced this quantity. So so we must apply the time evolution after we prepare the vacuum, and this should be independent of T if we can ideally prepare vacuum. But in practice, we have an oscillation as changing T. Yeah, since this is the only approximation. So this quantity seems to have an intrinsic ambiguity in our prediction by this method. And so we estimated systematic error basically by amplitude of the oscillation as changing time. And this error by the purely statistical error by finite number of measurements. And this one is a result of exact diagonalization. So it seems that if we take a good value of parameters, we get oscillation around the exact result. Yeah. So far we have only statistical error and systematic error, and this one is a plot of extrapolation to infinite volume and continuum limit. So, and of course we also have a total error. So we have a possibly 5 sources of errors. Yeah.
Okay.
Yeah.
Then why your estimated value is so good compared with the mass perturbation? So in the vicinity of wave equals 0, this cross sign is almost on the lines.
I see.
The error by is large.
Yes. This is a good point. We expect that we are overestimating systematic error. By this method, and so in this, for example, in this plot, we have a oscillation around the exact result, but the central value is not the same as the exact result. So we have some systematic. So we expect that we are overestimating the systematic error, and so we would like to have we are looking for better estimation, better way to estimate the systematic errors.
Thank you. Then can I ask a related question? So you said that your results are consistent with the tensor network, but it looks different because your error bar is overestimated, and red diamond is it looks different from the blue cross. So why you consider that your result is consistent with the tensor network?
Okay. For this particular point, sorry. Honestly, I'm not sure, and
I see.
if we Okay, another subtlety is that tensor network approach usually do not put errors in plot, right?
Yes.
Yeah, but I expect that tensor network approach has a very small errors. So it seems strange, but honestly, sorry, I have not pursued the origin of the difference. Yeah.
Thank you. By the way, this mass perturbation has some control parameter. So you control the value at the m equals 0, or this is no fitting parameter. Mass perturbation line.
This one?
Yes.
This one has control. So what do you mean by control parameter?
So this mass perturbation line is almost same with your data, but it's different from the tensor network. And so I wonder that there is a fitting parameter or
not. Yeah. Sorry. The result, we don't have no. We don't have a control parameter. So
okay.
Yeah. So this is the result for continuum limit and infinite volume limit.
Okay, I see.
Yeah.
Thank you very much. Very interesting talk.
Thank you.
Okay, next is Akiyama-san, please.
Can you hear me?
Yes.
Thank you for your nice talk. And I have a question about the effect of the dimensionality. Well, your calculation was done on the 1+1 dimensional QED. So if you extend your study to the 3+1 dimensional QED, what can we expect? For example, for the behavior of the potential, or the when we put on the probe charge with non-integer value.
I see. Okay, for three, I think 3+1 dimensional case is subtle, since we are not sure if the theory itself is well defined
Yes.
point of lambda 4. And in 2+1 dimension, so okay, let's see. So I'm not sure about the massless case, but well, and also the big difference is that Coulomb behavior is different from confinement behavior.
Yes.
Yes, in higher dimension. But
yes.
I think in 2+1 dimension, people usually expect the confinement behavior.
Yes.
Yeah. But I'm not sure if there is a similar rich behavior in higher dimension. Also, we don't, and another difference is that we don't have a theta term in 2+1 dimension. Yeah, but instead we have a Chern-Simons term, and Chern-Simons term may give a richer structure. But I don't have any good analytical approach in higher dimensions. Yeah.
Well, your approach is directly extendable to investigate the 2+1 dimensional QED or 3+1 dimensional QED.
Okay. In
with
principle,
a similar
yes.
setup.
Sorry. Okay, there are big difference. Okay, in principle, yes, but practically there are some difference. First one is in higher dimension, gauge field has a propagating degrees freedom.
Yes.
Yeah, so we needed to treat the physical Hilbert space of gauge field. So
yes.
So concretely, we have a some truncation of Hilbert space for physical gauge field. And another one is maybe if we use a Jordan-Wigand transformation, we should get a much more dirty lattice Hamiltonian. Yeah, but for the first problem, for first difference of gauge field, I think, for example, if we consider purely Chern-Simons theories in 2+1 dimension, we do not again have propagating degrees of freedom, and we do not need additional truncation of Hilbert space. But the difference appears when we put the kinetic term of gauge field. Yeah. So in pistol we can get regularized theory with finite dimensional Hilbert space, but I think practically we need a much more number of qubits, and so we have to wait the development of a computational resource for higher dimension. Yeah.
I see. Thank you very much.
Okay, thank you so much. Okay, so the time is over. So